Hey there, welcome to SkyTour LiveStream for March 18th, 2019. This is Mark D'Antonio, and I'm here with Daryl Mason hanging out in the background. Daryl, are you still around?
Yeah, I'm here.
There
Sorry.
he is.
As usual, I had to mute on.
Oh, no, that's fine. That's fine. Yeah, it sounds good. And look at this. Officer Rob is here, Marianne Robb from Arizona. How you doing, Marianne? Nice to see you here. Oh, yeah, and then that's right. Keith was simulcasting yesterday. He was simulcasting our show yesterday, wasn't he? That was kind of cool. So, yeah, so that's kind of fun. Tonight, this stream tonight is going to be kind of fun because I'm going to be at 1 o'clock is when the action starts here, 1 a.m. for me, because it's 1 a.m. Eastern. It's about almost... It's 22 hours, 48 minutes. It's 10:48 Eastern time here. And at 1 a.m. Eastern time, I'm actually going to go on Midnight in the Desert for 2 hours. So I guess I don't need sleep, right? Astronomers don't really sleep, do we? You know?
I sure do.
Yeah, but see, you sometimes will sleep during the day, too, you know?
Yeah,
and that's something
bad habit.
No,
I'm retired. I've developed. I really like my afternoon nap.
Yeah, see, and I mean that's kind of interesting, but that's what keeps you going for the rest of the night, yeah.
I guess.
Yeah.
I can't keep up with you young people anymore. I'm lucky if I make it to 11 o'clock. Sometimes when you do a stream, I think I've been around my time until maybe 12:30, and I can typically stay up to that. But I've become a creature of habit.
Yeah, I mean, we are habitual creatures, aren't we? You know.
I sure am. I know that.
Well, we're habitual creatures. I want to say hi to D. Smith, which I did in the chat already. I said hi to Marianne. And, of course, I said hi to you, Daryl. And I do want to say hi to Flames of War, who's here.
Hi, Flames.
Hi, Flames, yeah. And only on YouTube can people have names like that. And people are like, oh, that's Flames. Yeah. Oh, that's Rock. Oh, that's so-and-so. That's kind of funny. You know, kind of funny. But, yeah, this stream is just we're going to have a fun little stream tonight while we're actually waiting for... I'm waiting to do Midnight in the Desert tonight at 1 a.m. my time. So I've done it before, and I haven't done it with this current host that's on there now. So I'm not sure how that'll go, but I don't have any problems. I never ask for the questions up front or anything like that because, I mean, you got to be spontaneous, and it's got open lines too, so, you know, you can't plan any of that. So, and that's what'll be pretty cool, you know? So we are actually on a little open cluster here, and we're in the constellation of Puppis. Where's that? Well, I'll show you. Puppis is right... Okay, if we do this and pull out a little bit, you say, wait, I just see weird stuff. If I get rid of the data and put in the constellation lines, okay, and the mythology, you can see this is the... this is Orion's hunting dog. Orion's over here, you know, setting... There's Lepus diving into the ground. Okay, this is Canis Major with Sirius, the brightest star in the sky right there. And then right above it is the little dog, Procyon, and that's the name of that's Canis Minor. And Procyon is right there, that's the star. And this is Monoceros, one horn. This is the unicorn. There's a lot of stuff in there. And then we also have Puppis. And I spent some time calibrating the telescope tonight, so now the scope, you'll see, is aligned with the cluster. We've had the case the other nights where over here on the right you'd see that it said scope. Well, I fixed that tonight, and it took me about an hour to do that. I don't know why, but you know what? It's just better if we can do it. And it may not stay. It's pretty darn temperamental. But... right next to this cluster is another one that we're going to go check out right now. All right, and we'll just do that right now. We'll just move on over. And if we go back to our view, we should see that we're now shifting to the left just a little bit, and we are. And you'll see now that we're in a patch of what looks like dark sky. All right, but it's not really dark sky. This is a really interesting location, and I'll tell you why. because actually I'm gonna make this change just a little bit. I'm gonna bring us up just a bit. Okay, it might be too much of a bit. Yeah, I got this set too high, so I'm gonna change the setting here. 1 and 4 combination. That comes from memorizing what your handset controllers have for data. Anyway, let me. Where am I here? I got this. I got that. Oh yes. Let me turn down the music just a little bit. I don't know if it's loud for you guys. Let me know. I just turned it down a little bit. That C.D. Smith just complimented you, Daryl. And you're probably on mute.
Yep, you got me.
Yeah,
I'm sorry. I'm floating around on too many screens here and losing track of where I am.
I figured I'd wait it out. That's okay.
Yeah, sorry.
No, that's fine.
I'll try to stay on top of things.
You're okay. You're doing fine. And I did want to take this time to let everybody know that Daryl has added immeasurably to SkyTour Radio, and I really enjoy having him on with us.
You're embarrassing me again.
You know what? It's factual data. Just act like Spock for a little while.
Well, Spock's one of my heroes, so
Mine
I'll
too.
try.
Fascinating, Captain. So yes, and what I think we should do is, tell everybody a little bit about what we talked about last night on SkyTour Radio. We were having fun with cosmology, and cosmology is the study not of the little things. It's not the study of the stars. It's not the study of how they're made up or the chemistry. It's the study about the universe in the context of where it's going, how it's going to end up, how did it form, all the big stuff. That's what cosmology is about.
It is.
It is. That's right. Oh, I wasn't. Sorry, I wasn't.
Oh,
yeah.
Okay.
Yeah. Good day, James Dugan from Down Under. Nice to see you here with us. Great to see you. And I'm going to take a photo here. 8,010 seconds. The moon is fairly bright. It's up to the upper right, a little higher in the sky here. So we're not going to be able to take too long of exposures. We won't be able to get too many nebulae, but the one that I'm about to show you is one that we'll be able to see. And it's actually not as good as it could be. So I'm going to try and process this a little better for us. Do you see this little nebula right here? Unfortunately, the blue background color of the sky, which is due to the moon, that blue background color of the sky is interfering with the blue color of this nebula.
Oh, I see it now.
Yeah, it's a bit of a problem. But, if we actually, if we can do a little processing, I'll try to see if I can clean that up a little bit. And I'll do it right now. Okay, first thing, I'm going to do this. And then I'm going to do this. And now I'm going to try this. Let's see if this... No, not that way. It might not be the right color, but I'm trying to accentuate the planetary nebula. Yeah, I think that's about as good as we're going to get it with the moonlight. Actually, I can do a little longer exposure to show that, which I'll do. So here's what I'm going to do. I'm going to go back and do that. It's a really interesting little planetary nebula that we're looking at right there. And what's a planetary? Well, Daryl actually knows what a planetary is. I can explain it, but I think folks like hearing you tell them about things. Daryl, you want to talk about planetaries for a minute?
Oh, I can do that.
Bet you
planetary nebulas come when old stars, similar to the sun, for instance, when they, I don't know if die is the right word, but when sun-like stars get old, they blow off their outer atmospheres and become red giants and eventually turn to white dwarfs. But where they blow off their atmospheres, that puffs out into space and makes what we call a planetary nebula.
That's right. Yeah.
I assume when they were first discovered, they called them planetaries because they resemble planets. It may be oversimplifying, but it's good enough for me. And what we see is some really pretty things out there are planetary nebulas. M57 Ring Nebula M27 Dumbbell Nebula,
Yeah.
all Messier objects. This is a Messier object too, M46. It's a star cluster, but we see the planetary nebula there also.
Right there.
Anyway, those old stars, they blow off their atmospheres and turn into white dwarfs, and what's left make really pretty objects in the sky sometimes like this.
Yeah. Now, on moonless nights, we actually noticed that this object is a brilliant blue against the blacker background. Tonight, though, because the moon is out and about, I'd say, 35 or 40 degrees up that way, because of that, it's actually causing the sky to look blue for the same reason the sky looks blue during the day. The reflected sunlight is causing the molecules to absorb some of that light, and then they immediately scatter the blue component of the spectrum from the sun, and thus we see it like this. Okay, I know this looks sort of green on the screen, but that's because I'm doing some processing here. If I return it to what it's supposed to look like, it's going to look like this right here. Okay, so maybe the best thing to do is just knock this down a little bit, so you can see the cluster and then the planetary nebula right here, just a little better. It's really pretty, and that little tiny star that's right in the middle of it, right? Okay, in there. Let me just get there. That little tiny star right there, that is the star that is what is called the progenitor, or the star that actually sloughed off these outer layers to make this planetary nebula. Now,
that's the baby daddy.
That's exactly right. I've never called it that, Daryl. Never called it that. That's a good name for it too.
Yeah.
Yeah. So that's kind of what we're looking at here tonight. We're actually having some fun. Like I said, I'm going to be going on the show Midnight in the Desert at 1 a.m. my time, Eastern time. So if you want to come join us for that, it's open lines as well. So you could call in and, call me names or whatever. I'm sure they would love it. But controversial radio is always good, it seems. But I'm not encouraging you to do that, but just saying. Anyway, so this is cool. Now, in the sky, where is this? Well, I'll show you. If we go back to our view here, our planetary view, I've also got our mythology showing. And I'm going to cut that off and leave the constellations. If you want to see where the moon is, okay, all I have to do is go up a little bit, and you can see the moon is right there. Now,
right next to Regulus.
That's it. In fact, the Regulus and the moon are at conjunction tonight. They're the closest they're going to get to each other.
Cool.
So that's what we're looking at here. All right. And I think that Regulus is Alpha Leo. It's the brightest star in the constellation Leo. Being this close to the moon, obviously the moon is very close to us, relatively speaking. And Regulus, of course, is not. Regulus is 79 light years away. So if you take 25 trillion miles, which is 4 light years, the distance to Alpha Centauri, and you divide that into the 79 and figure out how many trillions of miles this is away, then figure out the moon is only 250,000 miles away. And it took us a couple days to get there. So, Regulus is a distant dream for us. But if we can go interstellar at some point, then that won't be as big a deal, because we will be able to do this. And that's something that is really a fascinating possibility. I like the idea of going interstellar, frankly.
Oh, yeah.
Oh, yeah, for sure.
It's interesting, Stellarium doesn't show Puppis as a constellation when it shows all the other, figures.
Yeah, it's kind of interesting. When we turn on the constellation lines, we have this, and if we look in Puppis, if we want to see Puppis, and we want to show the mythology, okay, we see Monoceros, okay, and this here.
They do. Okay, that's Puppis right there.
Yeah, but
may I say, Puppis doesn't mean dog or pooch or puppy. Puppis was the poop deck of the old constellation Argo Navis, and now we're seeing it right there, which it wasn't showing before.
Well, I turned the ground
Puppis
off.
is the poop deck, or the stern of the ship.
Yeah, you see the ship with the sail right here.
Yeah, you can see the sail, which is Vela, and Carina is the keel down on the bottom. That's getting pretty far down in the southern sky where we can't see it well.
That's right. Yeah.
But Puppis means poop deck or poop.
Yep.
Or stern.
We only see a piece of Puppis here when you hit the ground. Okay, this is my local horizon, right?
Uh-huh.
So you can see the cardinal points, south, southeast, okay, and then southwest. But we see a few things, and, you know, I'm actually looking at things that are really kind of close to the horizon. So with the moon out and everything, it's a fairly clear night for us to be able to see these at all, even with the moon's brightness. So turning off the mythology, we can go and bring ourselves up a little bit higher to check out a few other of the clusters up here. I
should add Argo Navis, the ship itself, was Jason and the Argonauts ship.
Was it really?
It was, yeah. You know, when they went off to find the Golden Fleece, that was the ship they took, was Argo Navis.
Oh, okay. See, that's the thing, you know, I didn't know that.
Well, now you do.
I know. Dee Dee is here. Hey, Dee Dee, how are you? Nice to see you. Well, I mean, see your name anyway, floating up the screen. I didn't see you because you're not visible on the screen at the moment. But it's nice to see you here. You can tell by the cams here that we have the telescope is pointing right out of the slot pretty nicely, and this is the long view from inside the observatory of the camera, or the telescoping camera. And in case you're not sure what you're looking at, this is the bottom. Oh, actually, I'm going to go in here and show you. Okay, this right here, this is the bottom of the forks that stick up and go into the page here and connect to the side of the telescope barrel there, and then they come up this side and attach to the side of the barrel there. Kind of hard to see. This is the actual bottom of a tilted plate that the telescope is sitting on, so that if you were to draw a line straight through parallel to the bolt that's right there in the middle, which goes straight up into the telescope basically, it would go straight to the North Star effectively. So that whole axis is aligned with the North Star, and then it switches and goes left and right this way in what we call right ascension, which is east this way and west that way. Okay, so it's actually kind of it's the way that all works very well. And that's kind of the architecture of the observatory, just so you have some kind of foundation to what that is, because I know that we haven't really talked about what these images show us. But if any of you have questions out there, I'm here, Daryl's here. I'm going to take this 15-second photo at 8,000 of this little cluster that's in, was it in Puppis, I think we're in still?
Yeah.
Yeah, this is...
I think. Yeah, M46, yeah, Puppis.
No, this isn't M46 now. This is... We're at NGC 2489, a little tiny, a smaller cluster, but that's okay. I think we're still in Puppis.
Very good.
Yeah, so let's bring that back. Hey, Stacy Johnson. Welcome to SkyTour LiveStream, where we do these clear night views of the night sky and take you on little journeys. Happy to do so, too. Okay, there's that cluster. Again, this blue is from the moon, okay, but it doesn't stop me from getting some nice views of clusters. We can actually knock it down a little bit of the blue. I noticed that the telescope has a little bit of a problem today, and I talked to the telescope maker, and I'm consulting other people, because what is called the secondary mirror on my telescope actually has some blemishes on it that are problematic.
Oh no.
Yes, the secondary is a problem, because that is internal to the telescope, and it's probably one of the more sensitive mirrors in the whole scope assembly. So I'm looking for a whole new corrector plate and secondary assembly for my telescope. And if I can't get it, then I will be forced to get an optical tube assembly, just the tube, for an F10 10-inch telescope, and put that on the forks that I have.
Huh.
So that's going to be tough.
Can you get an optical plate, a corrector plate and secondary without returning the scope to the manufacturer?
I called the manufacturer, said they don't have these anymore.
The F6.3, yeah, I'm not surprised.
Yeah, because they only made a short run of them. And I want to convert it over to an F8 or an F10. So, I mean, I could do that with I could put a lens in there to do that, of course, but that adds more distance back from the assembly, and that means that the camera could strike the telescope if it goes back enough, and I don't want to do that. Yeah. Hey there, Nikki. How are you? And Laura's here. Thank you. Good to see you.
Hi, Laura.
Tom Deep is here as well. And who did I see before? There was someone else. Stacy Johnson, I said hi to. Who else was here? Somebody else new. Papa Tom's here. Nice to see you. And I think I caught everybody. Not sure. I'm just looking for the new folks here. Orlando, Florida. Nice. You got nice weather down there. Actually, if it's clear tonight down there, Nikki, I wonder if P&K Science is actually streaming tonight. Usually they do if it's clear. And, you know, P&K Science, SkyTour LiveStream, which is us, and Bill New York Skywatcher, we all stream together, and we have a website as well as a YouTube channel. The website is called Astro Imaging Live, and I think that's a site where you can go. I know it's a site where you can go to see all three of us when we're streaming together. You can go there to see it, and we're actually working on that site to make it automatic. When we stream, it just goes up there automatically. And hey, Brian Bruce, you know what? You're the one that was asking a question. He said about the ripping of atmosphere. I'm not sure what you mean by that. Does the atmosphere freeze, or what happens? Under what conditions, Brian? I can tell you this, and you can tell me if I'm wrong. When we talk about the atmosphere, well, all atmosphere can freeze out and fall like snow. It just depends on the temperature. And in the atmosphere, I mean, temperature and pressure play a major role, of course. So if we think about, like, for instance, carbon dioxide in the atmosphere, if we can get the atmosphere down to like minus 109 degrees, which you might think is impossible, but it's not, because the coldest place on Earth was down in Antarctica at a place, a drill hole actually, called Lake Vostok. Actually, a Vostok station, and they were drilling into a lake that was a couple miles beneath the Antarctic ice. And this lake down there actually has over 3,500 different types of life in it. A life that's never seen the light of day for millions of years. So, life, as they say, will find a way. Well, it sure does. Well, it was minus 129 at Vostok Station. That's the coldest temperature ever recorded on planet Earth. And it was at Vostok Station. So if we were breathed out at that point, as you breathed out, the carbon dioxide would freeze in your mouth and fall out as snow and frost on your face. And you would actually, it'd be a very miserable way to go.
It would.
Yeah. Marianne, thank you for coming. Thank you for coming by. And here's one happy guy. Thanks for coming by. Good to see you. Sean Hawkins, Mendocino, California. Oh, man. Cloudy till May. I don't like to hear that. That's no good. You know? When the planet explodes? I don't think Brian, you're saying I was talking about when the planet explodes. Did I talk about when the planet explodes? I don't remember talking about that.
I don't remember that.
Yeah, you don't either. That's okay, Brian. Just let me know what where you're going with that, and I'm sure I can figure out what we were talking about. I'll try anyway. So, let's see.
Coldest I ever saw was 42 below zero Fahrenheit. It was minus 48 a couple of miles up the road.
Wow.
That was more than enough for me. Thank you very much. That was up in the high country here in Colorado a long time ago.
That's instant freeze.
It is.
Instant frostbite.
Once you get to minus 30, minus 35, breathing becomes a whole different thing. It feels like you're breathing champagne. I always thought. It was so cold that day, though. My brother-in-law took off for work in his old Datsun or Nissan pickup truck.
Yeah.
He got about a mile down the road, and it was so cold, one of the axles snapped on the truck.
Wow.
And he started doing donuts down the highway.
Wow. That's cold. That's cold. We're gonna go to this cluster here. We're just visiting all these little clusters that are just east of the star Sirius in the sky, the brightest star in the sky. And we're gonna go here now, and you'll know we're going because you'll see the telescope crosshairs show up. There they are. Boom, and they line right up, and there they go. See, they're doing it. The telescope's doing that automatically, which is nice. I took the time to align all that today to get that up and running. And this is just a little, like I said, a little cluster. And I have to look at the sky here and make sure, not just figuratively, not going out yet into the sky. I might be a little too far over at the moment, because I was actually having the dome opening right about here, and it might be just a little too far over right now. But I wanted to get, I wanted to be able to get the moon, which is up here. Okay, I want to be able to get the moon, little moon, it's up here. Where'd it go? Why is the moon not here? Did I turn the moon?
Somebody stole the moon.
I must have turned it off without realizing it. Oh no. Okay, well I turned off the moon. So, can you all go outside and see if the moon's there? Just kidding. But it doesn't matter. We certainly know that the moon is still. We know the moon is still there. Okay, so now this is that little cluster, and it's way down by the horizon. But we're gonna check it out and see what it looks like, because I think it's kind of cool. And we'll see now. But I'm gonna come back and go here. All right. And you can see that its telescope is moving, getting into position. And when our north, south, east, and west come back, that means the telescope has stopped hunting, and it has. And there it goes. Alright, so now let's take 15 seconds at 8,000. Actually, I'm going to bring it up a little bit because I have a feeling it's down there. We'll go right to there. I could be wrong, but I'm going to just check it out anyway. So now we're taking this picture of what should be this little tiny cluster over here, and we'll see what we got. You know, I kind of like these little clusters. And we'll see what we get. So, okay. And again, unfortunately, it's very bright from the moon. So there's the cluster. It's up there. So I should have just trusted the telescope, and I didn't. My mistake. My mistake. I'll do it now. I'll trust the telescope now. And let's do this. Bring it down and head over a little bit toward the west. Okay, now if we take this picture and make sure the telescope is steadied out, we should see that little cluster in there. Nikki, I'm right there with you. Nikki says, I love learning about this and want to know everything there is to know about the heavens. You know what? You and me both. I started learning about it when I was 9 years old, and I just couldn't get enough of it. I still can't. You know? Yeah, we're looking at a really, it's not so dark down there. We're getting a lot of issues down there. I think actually there's probably a cloud bank way down there that might be interfering. So let's not try to go down that far. Let's just try to move up a little bit can see some other things here. First of all, let's go check out this star pair here. These are interesting because this star pair is actually they're pretty. It's a pretty star pair in the sky. So we'll check it out. And you can see the telescope is coming in. And there they are. There's that star pair. I'm going to show you something else too that we do with this. And it depends on this telescope control being up. You know, when we look at stars, you know, we don't know, you know, we can't tell what the colors are just by looking at them, see? However, we can figure them out if we do an interesting little trick. And here's what we're going to do. We're going to go to 15 seconds. This is it. Let me just actually bring us to that. So 15 seconds, all right, at 8,000 sensitivity. That's ISO. Oh, Nikki, thank you for coming by. It was really nice to see you. You have a good night. But I'm going to turn off the tracking, and you'll start to notice that basically I've turned off the telescope. And now look, you're watching the Earth rotate out from under the stars. This is the actual rotation of the Earth that's actually causing that. Isn't that cool? I mean, it's such a small thing, but it's such an important thing. And now we're going to actually take a photograph while it's moving like that. All right. Now the image freezes at the moment, okay? But when it comes back, you're going to see something interesting. All right. And when it comes back, we're going to turn back on the tracking. Okay, here it comes. We turn back on the tracking. All right, and we go to the image. Okay. And now you'll notice that we actually have a little, I'm going to make this a little easier to see. Okay. You'll notice now that we actually have a little bit of color difference between these stars. Now it's hard when the moon's out, okay, but you'll notice that by turning off the tracking, we get a streak, of course. And this is the amount that the Earth has moved in 15 seconds in our particular telescope. So you can see that you can't take an exposure in this telescope with the camera for any length of time without making sure that the telescope is aligned and properly tracking the sky. Otherwise, you're going to get streaks like this. But you can see that we have different colors here that we could not tell before. This is more of a white, and this one's more of a yellow. Okay, very interesting. All right, and I think that's sort of indicative of the many different colors we see in the stars. And of course, by a property known as Wien's law, we can figure out the maximum color, basically, that's coming from a star, and figure out the temperature associated with the star, in part. And I think that's pretty cool. Oh, Nikki, are you kidding me? You belong here, man. You belong here. You have a thirst for knowledge. I love it, and I want to just welcome you to the SkyTour LiveStream. Thanks for coming. And Brian Bruce, if I didn't quite get close enough on your question, let me know, and I will. Because I actually did a talk. I do a lot of talks, as you guys know. I did one talk on what would happen if the sun went out, and I mentioned this yesterday on a show, and it is that if our show, I think today's Monday, right? I think so.
It is.
Oh, thank you. So, when if the sun went out, we would only be alive for 7 days, at the most, because it's only after a couple of days the temperature would have gotten so cold that the oceans would be permanently frozen, and the atmosphere would start to snow out of the sky until there was none. And it would be so cold by the end of a week that there'd be no humans alive, because there would be nothing, any power that they had, the power grid would be down, no way to stay warm. The only way they could stay warm is if they could drill a hole deep enough and put a bunker deep enough on a geothermal hotspot that they could get some heat. But that would just be prolonging the inevitable, because where are they going to go? They can't they can't survive, you know, in the long term. And that's you know, that's why we like our planet the way it is. We don't want to actually, you know, we don't want to have any problems here. But, you know, someday the sun is going to swell into a red giant. When that happens, well, then we're not going to worry anyway, because we will not be here. You know, we will, of course, have to have left. Okay. I'm going to bring us to the butterfly cluster now. Okay, and we're doing that. And there's a reason. And we'll do this as I come here again. We're going to do that. Check it out. And we pull into the butterfly cluster now. You see the telescope is pretty good here. We're okay here, you know, as you can see. This is the observatory cam 1 and observatory cam 2. This is operations, dome ops, where I am. And this is telescope control. Okay, good. So we're set there. And I'm going to do 15 seconds here at 8,000 again, and see the resulting photo of the butterfly cluster.
Dome ops would make a pretty good handle. Pretty good mix.
That's true, huh?
Yeah.
Who are you? I'm Dome Ops. Oh, wow.
I am Dome ops.
Dome Ops, yes. Is that Dome Mops? M-O-P-S? No. Oh, this is cool. So yeah, I'm seeing see, here's a problem we have, and I'll take care of this in a moment. As the temperature changes, we find that the focus changes. Okay, so you'll notice that in this image, these stars look like they're not quite focused. Now, earlier tonight they were, but the temperature has changed. In fact, unfortunately, it's gone down. And the temperature changing like this causes the focus to change in the telescope as all of the metal and everything in the scope contracts. Now, we can get around that by just heating the dome, right? Yeah, no.
It doesn't work like that.
Yeah, it doesn't work like that. You're right. We can't heat the dome. We can't heat the dome because, of course, then the heat waves will go rising and going out of our opening in the dome, and that would cause the image to go all wonky and just shimmering all over the place, you know. So I think it's pretty cool. And once again, Nikki, thank you for coming. I know it is addictive. You want to see what's going to happen next. I totally get it. I'll tell you what, for the next 5 minutes, Nikki, just think of it this way. We'll just look at this out of focus cluster. So it'll be boring, so you can just go to bed and then come back the next time we start up, next time we're clear. Okay. Just don't anybody tell her we're actually going to move on to another cluster now. I don't want her to feel bad. Just kidding. You have a good night. So, always eat DW's here. Nice to see you. So I'm going to come back here and take this guy, and I'm going to just move him over a little bit. Because what I like to do is I'm going to actually see if I can focus our camera just a little bit better. To do that, I'm going to zoom in a little bit here. Sort of a focus mode. Right. And I'm going to work on doing a little more than this at some point, but I'm going to try and focus now a little more. And you'll notice if the focus goes out, you can tell. All right. But if I do that, notice if I go way out of focus, it's kind of hard to see, but you see the little rings. The central dot in there is actually a secondary mirror that's in the telescope. You're actually seeing some of the structure. All right. So as I bring the focus back down, suddenly all the rest of the stars just like wink into view, you know. So that looks pretty cool. I'm not sure if that's the best focus, but I'm gonna see. I might have just gone past it a little bit. Let's try that. Yeah.
Mark,
Yes, sir.
Brian rephrased his question. Would you want to tackle that?
Okay, sure. But I was thinking, when a star goes supernova and the planets that are close by, okay, explode, does the atmosphere turn to... Okay, that's a better question, Brian. Now I get it. Brian's question is, if a star goes supernova and it has planets in the system, basically what happens to those planets? If you think about it, what is a supernova? A supernova is a cataclysmic explosion of hot plasma that's blowing outward from the star, at speeds of like 8 miles per second. All right, and that's 28,000 miles an hour, I think. So if that happens, what will happen to the planets is that this radiation and this excessive heated material, this plasma, will rake across the planet, and on the side that it hits, it will actually disrupt the atmosphere and also boil away oceans and so forth that might be on that side. Basically instant death for anything living on that side. If that's the case, we'd find that we're having a kind of a pretty disastrous day, because the far side will get the wraparound effects of this plasma, and the plasma will punch through the magnetic field because there's going to be so much of it. It'll be like a flare that is just unforgivably large. And we haven't really seen any unforgivably large flares here yet. See, this is much better focus now, see? So, these flares like that, we have X-class flares, which are pretty much very, very high-end flares. And we have other flares that are lower intensity. But I can tell you that the sun, being, a ball of hot gases, okay, most of the sun is just hot plasma, and it's only in the core of the sun where the nuclear reactions are taking place. All the rest of the sun is heated by the fact that these reactions in the core are transmitting energy through the gas outside the core, and that transfer heats the star up immeasurably. When I was getting my degree in astronomy, and I told this to Daryl, and I told some of you, I think, we actually had to create a computer model of a star from the core all the way to the outer spherical, where the atmosphere of the star ends. And it took us 3 months to do it, because it was a very extensive thing, and we had to do this as part of our project work for getting a degree in astronomy. And it wasn't easy. It was extremely hard, but I had a star. That was radiating radiation from the center in my computer model, and then as it went outward, I made the star I made the star kind of an older one, so that the outer atmosphere was actually convective, like a pot boiling with water, and that convection would move material from near the core all the way to the outer envelope of the star, all the way outside the star. So you could actually see stuff that the star made near its core, okay, showing up on the outer envelope. But it wouldn't get there for, like 1 million or 2 years. Because not because the star's so big, but because as stuff is trying to move out, it's colliding with other stuff, and it just can't get out. It's like being in the ultimate crowded room. Really interesting project. And the scientist that we based our star model on was named Eva Novotny, and her book that we had to follow was Stellar Atmospheres. I gotta tell you, and there probably wasn't a whole lot of interesting talk around her dinner table at night, I could imagine. The book, of course, was very dry because it was just totally all science. But Novotny's book was sort of a model for looking at stars and stellar atmospheres. This was, of course, before we knew that neutron stars merge, before we saw black holes combine, before we saw gravity waves or anything like that. So we didn't model any of that. I would have liked to have modeled like twin neutron stars orbiting each other and then colliding, and seeing if we could catch the outflow of material and or waves. I think that'd be really cool. You know, very, very cool.
Mark, may I pass on something from chat? Dew is asking for your email address. He wants to send you a picture. I don't have your address, actually. Would you want to post your KGRA email address or anything?
Sure, I can. Do you have it?
I do not, no.
Oh, okay. Let me just poke it up there.
I'm not Amanda, sorry.
No, that's okay. Yeah, we have our own email now at KGRA, which is great. KGRA gave us this email because our show was actually quite popular. I was very surprised. And again, KGRA is a paranormal radio station, so I know when they said, you know, you got to try and you got to do your show, you got to do a show on KGRA. I was like, I'd love to, but you're paranormal, and you know, your audience may not like what I do. Oh no, they'll love it. They'll love it. That's what I was told. So I kind of, with some trepidation, I did the radio show, and I found out that you guys are amazing. You guys enjoy it, and some of you listen to KGRA, some of you do not. We're going here right now, okay? And I think that that's sort of a a beautiful thing, because you guys are actually very intelligent. You ask great questions, and you know what? That's the thing. I don't ever duck any questions. I'm not afraid of questions. In fact, when I do a show or something, I don't ask to see the questions ahead of time. You know, I'm not one of these little prima donna type people that have to have all the details ahead of time, so I look the best I can. I mean, if there's something I don't know, then guess what I say? I don't know. When did we forget to know? When did we forget about how to say those words?
I said that last night.
Right. Yeah. Right. But you know what? Most of these prima donna folks out there that are, you know, stars and so forth in Hollywood, okay, and watching those guys, they're afraid to say, I don't know. You know? So it's pretty crazy. Thank you, Dew. I see your note. I'll check it out. You know, we're going to take a picture here because I want to show you. This is an orange star that you're seeing right here. And this is a star that's a brighter whitish blue. And I want to show you the difference in the colors here. Okay. Now, you'll notice that actually this kind of helps. We had a little bit of the image walked a little bit, but we can actually see the difference in these colors, which is kind of cool. And it actually helps you figure out the brightness too. But I want to show this. I want to show this a little better. So we're gonna go here, and what I'm gonna do now is bring my little control panel up. I'm gonna bring this over, bring it up a little bit actually. And now what I want to do is I'm going to turn off the tracking. All right, tracking's turned off, and as I said, we're literally watching the Earth rotate. Okay, and now I'm going to take the picture. Okay, now as I take the picture, now the star's going to trail, and that trailing is going to help us see the color even easier. All right, and so when it finishes trailing, when it finishes the exposure, I mean, I'm gonna turn the tracking back on now, and then head over to here, and you can see now the color of the stars very clearly. Here's one that's nice and blue. These are sort of dimmer. This one's a little bit red. This one's a little bit blue. This one is sort of a bluish white. This one is a brighter white, isn't it? And then this one is kind of an orange. Isn't that fascinating? I mean, so that's one way to see the color. The other way is to defocus the image. And when you defocus the image, it's you see that round donut like I showed you earlier, and that defocused image will actually be colorful as well. So, but if you let it stretch out, you see the color as well, and it's very good at showing you the brightness. Now, if the moon wasn't out, you wouldn't see blue here. This would sort of be a much darker background, okay? And so with the moon out, there's only so much we can look at, but that's just the way it works, the way this is. So not sure, not sure what the best way to show star colors is, but we can do one thing. When I have a spectral system now that I've been testing in the dome, and it's a whole nother system, a whole nother camera, and that takes spectra of the stars, so we can actually see what's in this star's atmosphere. We can see what's in this star's atmosphere, this one. We can actually look at the spectra of these stars, and it's really interesting to do that, because it's through looking at the spectra of the stars that you learn what they're made of. And why is that? Well, remember I told you how the only nuclear reactions in a star are in the core, and that heating of the outer envelope of the star occurs because of the fact that that radiation from the core is radiating out for billions of years. Okay? Well, effectively that outer envelope is a lot cooler than the inside of the star. The inside of the star is going to be anywhere from 13 million to well over 100 million kelvins. Okay, and 13 million is like what, 25 million Fahrenheit. So you can see it's pretty hot inside a star. So relative to the core, which is the hottest part of the star, the outer envelope of the star, warm as it may be, is still cooler than the interior. And it constitutes, for us astronomers, it constitutes a cooler gas. And what happens when that hot radiation comes through a cooler gas is that cooler gas absorbs some of the energy. Well, we know it does because the outer part of the star is very hot too. Okay? And that absorption of energy results in a little bit of the star's spectrum being affected by the particular element that's in that outer star's atmosphere, and that is absorbing that energy from inside the star, the higher energy from inside. And so what we see is a dark line, a dark vertical line in the spectrum of the star. And the star spectrum will actually look like a band like this, and then there'll be dark vertical lines in it. These don't show it because I'm not doing this through a spectral system. Okay, but you'd see a dark vertical line, and those vertical lines appear in specific places for specific elements. So hydrogen, for instance, has specific locations in the spectrum where lines will show, these absorption lines show. Okay, and I can show you hydrogen alpha, beta, gamma, and delta lines, and hydrogen has many of them. And in fact, hydrogen has different series of lines. The hydrogen alpha, for instance, is the red we see in the nebulae when we look at nebulae, okay, like the Orion Nebula. And that represents a part of what's called the Balmer series, B-A-L-M-E-R. And the Balmer series is it's a series that's based on electrons that move from one spot in the atom to another specifically, and that other is level 2 in the atom. Okay, energy state 2. And here's an interesting bit of trivia. Atoms all have these quantized or specific and discrete energy levels in them, and these specific energy levels, because they're so discrete and quantized, this gave rise to the term quantum mechanics, which is the study of atomic structure and atomic interactions. And so quantum physics is the study of the atomic structure and all the many transitions from one energy state in the atom to another discrete energy state in the atom, and so forth. So that's what quantum mechanics is, see? So you don't even need a degree, you now know what it is. So, but the fact is, these discrete states, these discrete things that happen, is specific for particular elements, and for particular energy levels that the electrons in the atoms go to in certain transitions, as they're called. So when an electron is ionized because of ultraviolet radiation, say from inside of a star, it could leave the atom. That's what ionizing means, that the electrons bounce off the atom, and the atom is left with a positive charge because protons are positively charged. Protons are in the nucleus. Electrons are negatively charged, and they are surrounding the nucleus. Notice I didn't say orbiting the nucleus. The little thing about electrons is that they're everywhere at once. And that's another one of those things you have to just sort of accept. It's nothing that I can make intuitively understandable. It's like a cloud more than a particle. That said, when these electrons get enough energy, they literally leave the confines of the atom. They're no longer bound in any one of the shells, okay, or energy states that are characteristic of atoms. That said, this means that they can then recombine with the atom if they lose energy by colliding with other particles outside the atom, and they do. And by dropping back into the atom, that's called recombination. If they drop to a particular energy state for their final location, then this is a particular transition from outside to in, and it's a well-known transition. Every transitional state in an atom is pretty well known now. And the Balmer series, the ones that I was talking about before, those are all the transitions that start wherever the electron is outside the atom. If it comes down into the atom and ends at level 2, numeral 2, that becomes a Balmer series transition. And the Balmer series is from any state above 2 down to level 2. Well, there's a Lyman series as well, okay? And those are to other states and to other, from anywhere else to other states in the atom, other levels. So that's what happens in atoms. They have these very quantized or discrete energy levels, every one of them. And as I said, that gave rise to the term quantum mechanics. So when we look at hydrogen in the star's envelope, hydrogen is the most plentiful fuel. So if we can examine hydrogen, we can actually see that we can examine other elements as well. And stars that are made, say stars that are being made right now in the Orion Nebula, because the Orion Nebula is a stellar nursery, as is many other nebulae out there that we see in SkyTour LiveStream. These nebulae will give rise to the stars, and they themselves have a rich supply of materials and elements from other stars that have gone supernova in the past. And that stuff ends up in these rich locations, and when a star is made in those rich locations, they're mostly hydrogen, but they also have a healthy supply of all these other elements. And those elements end up in their outer envelope. Okay? They don't ever fuse, they end up in the outer envelope, so that's what the star's made with. Think of them as pollutants in the star's atmosphere, basically. And the only way we ever see them again is if the star goes supernova or creates a planetary nebula and sloughs them off into the interstellar medium. So it's kind of interesting how that all works. That said, that's kind of... we sort of talked about that yesterday, I think, on SkyTour LiveStream. Didn't we, Daryl? I think we went through the end of the stars.
Yeah, we did, yes.
Yeah.
You know what, though? You talked about our sun and Earth-like, Earth-like sun stars, and you talked about bigger stars. You didn't talk about the smaller stars, though. What's their fate in the universe? Mark, I hate to interrupt. People are saying your screen is frozen, but they see the clock moving. It looks fine to me on your end.
Maybe I was too long in this screen, so they thought it was frozen because they think maybe this is movement.
Oh.
Okay, that's actually an interesting thing, folks. I was going off on stars. I should have come back to a live view so you can actually see, because I wasn't moving the cursor that much either. So, if the clock was moving, then it wasn't frozen. I just had you on a still screen, so I apologize for that. Feel free to demote me 2 steps and send me back to my post. I'm sorry.
I'm sorry to interrupt you, but yeah, I said a moment ago, you know, last night we talked about sun-like stars, sun-like stars, and
Yeah.
larger stars. We didn't talk about smaller stars, though. Their fate in the universe.
Yeah.
I guess ultimately, you know, from a cosmological point of view, what you're going to wind up with is white dwarfs to black dwarfs and maybe red dwarfs, because red dwarfs can live many billions or even trillions of years, according to scientific guess, I guess.
No, you're right about that. And
yeah,
well, you know, let's talk about that for a minute. Okay, we have a stellar classification scheme, which goes from hot blue stars that are big giant stars, they only last a few 100 million years, all the way down the scale to these tiny red dwarfs that are only slightly bigger than the planet Jupiter even. We've even found a star smaller than Jupiter. But of course it's more dense, has a lot more stuff in it, so it can reach those temperatures it needs to go nuclear and undertake fusion. But those stars at that low end, they're only like 2,500 Kelvin or 3,000 Kelvin. Our sun is 5,000 Kelvin, and you know, there's the hotter stars are 40, 50,000 Kelvin and more. And so this is what happens. That the stars are the smaller the percolator. Is what I say. The smaller the percolator, the longer it'll last. Our sun is moderate sized, so it's going to live another 2 to 5 billion years. Small red stars, they could live trillions of years. Trillions. So think about it, took 4.6 billion years for life to develop here on Earth. Screen's not frozen, by the way. Okay. Took 4.6 billion years for life like us to arise here. So the question is, what would happen if we were around the red dwarf, which is one of those little tiny red stars? Okay, well, what would happen is we would end up finding out that we have a much longer lifespan that we'll have on those planets as a species, potentially, because our star is not going to destroy itself for many millions, billions, and trillions possibly of years. And that's kind of a very interesting finding. I think that, considering that some of these stars last that long, I really think that we'll probably find that life can probably exist around one of these stars in a very, very, I'd say, docile way. I mean to say, in a way that would actually probably eclipse us in our evolution, because if there's life forms there, we're going to find that the creatures that live there are going to have the ability to evolve in a whole different path than we did. Part of the reason is because the planets around these small stars, that are only a little bigger than Jupiter, they have to orbit really close to the star to be in what's known as the habitable zone. And that's the zone that we've identified for life like us, is the zone where you have liquid water that can stand on the surface and pool, like an ocean or a lake. And that pooling of water, that ability, is something that will allow us to survive, because we came from the water. We came from the ocean, actually. And when people doubt that, all you have to do is lick your skin, and that's salty. You actually carry a little bit of the vestigial salty ocean with you from your evolution. And I've shut a few people up with that. They trying to tell me that we're alien seeds. That may very well be true, but the evidence against it is pretty hefty. So that's kind of interesting. Hey, welcome, Dr. Mark. I see he just arrived. But these red stars are small percolators that can last trillions of years. So the other problem is the planets that circle them being so close. There's another phenomenon that we've talked about before, It's the same phenomenon that we see with Mercury and the sun. Now, Mercury is almost fully tidally locked to the sun. It's not quite. Okay, and what does tidally lock mean? Well, it means that the same side is going to face the star. Okay, at all times, in the same way that the same side of the moon faces us. So that tidal locking process is going to cause a different evolution. And that difference in evolution will be, for instance, that on these planets like this that are around this beautiful red star, okay, they are going to, I'm going to take this picture here, 15 seconds, at 8,000. These planets around red stars are going to be, that are tidally locked, are going to have a perpetual sunshine or tropical paradise, perpetual sunset vistas, and perpetual nighttime starry skies. You know, but the only problem is that these planets, because they're so close to the star, are also going to go through their year very quickly. And what does that mean? It means they're going to go around the star in probably just a few days. If we look at TRAPPIST-1, one of the planets, planet E, as a matter of fact, that we think might actually be habitable, it goes around the star in just about 6 days. So that's its year. So if you talk to like one of the inhabitants on TRAPPIST-1, who's like, say, 40 Earth years old, okay, well, he's going to be hundreds of years old on TRAPPIST-1 because his year is going to be 6 days long. The other thing that is interesting is if you look out at the nighttime sky on TRAPPIST-1, again, you're tidally locked, so the whole planet is moving around the star. It's not rotating. So when we turn the tracking off here in SkyTour LiveStream, okay, you've seen what happens, and I'll do it again just to show you. That's a beautiful little cluster, by the way. So we have, you can see stars here, right? Well, if I turn off the tracking by doing that, we see the Earth rotating, and you can see it as the stars now migrate past my pointer. Okay, you're actually watching the rotation of the Earth as we rotate out from under the stars. Okay, now that said, on a planet around, say, TRAPPIST-1, we're also going to see that happen, but it's not going to be because the planet is rotating. It's going to be because the planet is moving around in its orbit around the star, and we're seeing a new vista. You know, as every few minutes goes by, we're actually seeing the stars from that we would have to wait like another month to see. We would see them sooner. Remember, Daryl in SkyTour Radio yesterday talked about the Wheel of the Stars, where as the Earth goes around the sun, our nighttime side faces a different spot, a different place in the universe as we go around in our orbit, and that's why we see different stars through the course of the year. Well, those types of things would happen around these tidally locked planets in 6 days. So you could literally, if you want to wait for the summertime sky, which of course makes no sense around these planets, but if you wanted to wait for the quote-unquote summertime sky, you might only have to wait 3 days. You know, and for us, we have to wait months. You know, so I get that that's what happens. Now, when these small stars run out of hydrogen at the end of their lives, they very quietly swell up into red giants, just like any other star. They don't go supernova, and they end up as white dwarfs in most cases. The only reason they might not is if they end up being eaten by a black hole, or if they're a binary star in orbit around another star. It's possible that they could be having material pulled off of them by the other star, and that could cause all kinds of problems, you know. So there's a lot that could be going on there, but most likely, if the red dwarf is just, you know, sitting there percolating, then we're looking at a future white dwarf. You know, swells up into a red giant. Last fusion materials go away, the star slowly collapses, and goes down to a white dwarf. It can't go any smaller than a white dwarf because it doesn't have enough mass to collapse further, right? And when a star dies, it collapses into a white dwarf. Or if it's more massive, if the core of that star that's collapsing is bigger than 1.4 solar masses, it'll collapse into a neutron star. And if it's bigger than 2.01 solar masses, it'll go past white dwarf, past neutron star, and to black hole. Very interesting findings in the world of astrophysics and black hole physics. So that's what happens. See, so it's pretty cool. So Daryl, to answer the question, it's just a white dwarf. You know?
Yeah. Well, I just it occurred to me after the show last night. You know, we talked about the big ones, we didn't talk about the little ones. So
no, we didn't. You're right.
But you know, getting back into that cosmological look at things, I guess the last warmth in the universe will be from the white dwarfs, and then they'll cool off and turn into black dwarfs, and everything will be blackness.
Right. We'll have a universe full of dark cinders, basically.
Yeah, cherry thought.
Yep.
Oh well, it's been a good run. I guess we got a couple of billion years left.
Well, I think we have probably several tens of billions. We're 13.8 billion now. Actually, 13.799. Let's not rush things. But you know what? We've been doing okay. I'm gonna just take the telescope and halt its motion because we are where we want to be. I'll come back here. Now I can actually show you where we're looking because I can just go into this 4K video mode. And again, because the moon's out, we may not see exactly what I want to show you, but we'll try. So we increase the sensitivity here, and yeah, we're not seeing it too well. It's right here. But anyway, this purpley red here and along the bottom and top, that's something that's part of the camera. It's actually what's called amplifier noise in part, and very sensitive cameras like this will often have such issues, which is okay. You know, I don't have any problem with that. I prefer it. I'd rather have a sensitive camera than one that's not sensitive enough. So 15 seconds at 12,800 sensitivity. And as for those of you who haven't been here before, I would like to say to you that this camera can go to a sensitivity like like no tomorrow. Now you've seen your cameras; they go, you can use 800. You can use, that's a pretty little cluster. Look at that, 800, 1,000, 1,200. You can go to 3,200 on some cameras, and even 6,400 on some cameras. This camera goes to 409,000. So we can easily turn a dark night into an overblown bright white image very quickly. Here's a beautiful little cluster. What's interesting is this cluster is not named, and I'll show you. I don't know. Let's go back here for a minute. Okay, you can see it's here, and it's unnamed. Isn't that wild? So, I mean, we should lay claim to that and say, hey, we want that to be SkyTour cluster. And we'll start a catalog. It'll be the Daryl. It'll be Daryl 1.
Not me.
Oh, you don't want that?
No.
No, come on.
I'll take a comma with my name on it. Comet Daryl sounds pretty good, but I don't want a star cluster.
Oh, you could be Comet Mason.
Yeah.
Yeah, periodic Comet Mason. Hey, that'd be kind of cool.
Yeah.
We'd have to watch that every year and have like a party, have a Daryl Mason party every time we saw a comet with your name on it. No, what wouldn't it be an excuse to have a party, right? We'd love it.
Any excuse for a party, I guess.
Well, in astronomy, especially if you're in the cold dome. When I was working in the professional astronomy observatories, the dome was going to have to be as cold as the outside air, because otherwise the telescope could, expand and contract. And even moving the telescope, especially in a dome that had a large telescope, I worked with a large, what's called an Alvin Clark refractor. It was 20-inch diameter lens in the end. And Daryl always says I'm making him feel.
You're making me feel jealous.
Yeah.
I'd love to get my hands on that for a night.
Well, if you come out here, I will bring you up there and set up something to view if we can. Someday, yeah. But no one comes to Connecticut to do astronomy. However, I will tell you this, and I'll finish the story about the refractor first. Then I'll talk about the lights. I worked on this 20-inch telescope for several years, doing part of the parallax study. And parallax is studying the distance to nearby stars, all right, and clusters. And we would take photos of the clusters and stars that we're looking for in particular, stars usually, and we would take very, very accurate photos, and we would then send those down to be measured at Yale University because they had a special measuring engine down there for doing this. And we'd get a statistical value for where the star's position was. And then 6 months later, we would do it again in the same star and send that position that we got, or get the position from Yale again, and then use the difference between those two to calculate the distance to the star. It can be very accurate. So I think that's pretty cool. And I think that's something that I would love to I'd love to pursue again, but we can actually probably do some version of parallax study right here in SkyTour LiveStream. The telescope is not, it's an instrument you can buy off the showroom floor, so to speak. But what you do with it is what makes the difference, So there's a lot you can do, and I know that astronomy for me, it's just amazing. I like I said, when I was 9, I knew I was going to be an astronomer. And the biggest thing I didn't like was the fact that more and more streetlights are going up everywhere I looked, and I hated that here.
Oh, don't get me started.
Oh, well.
I used to belong to the International Dark Sky Association.
Yep.
I banged the drum about light pollution locally here. And the city did switch to full cutoff sodium gas fixtures, or sodium light fixtures, which helped, but it was only temporary. The city's grown tremendously around me, and it's a losing battle, I'm afraid, light pollution, which most people don't care about, most people don't know or understand. And so many people around me nowadays, they light their properties up like prison yards.
Yes.
And it's objectionable, it's ugly, and it's ruining our night skies just when we're really getting a handle on what's going on out there.
Yeah.
And I personally have little hope for the future as far as light pollution goes.
Yeah, I'm a little different because I've actually watched my skies in Connecticut get darker. Since 2012, this state, and part of it is due to the university that I got my degree in, we lobbied the International Dark Sky Association to work with the Connecticut legislature to make Connecticut a dark sky state. And believe it or not, this hub of activity between Boston and New York is a dark sky state. And you can't get state funding to put in new lights unless they're full cutoff fixtures. So you can't put lights on the ground aiming up at your sign, okay, because that light spills off and goes up into the sky. And the sky is recognized as its own ecosystem. And to keep it healthy, it needs to be dark. And on my street right here, the SkyTour LiveStream John Zech Memorial Observatory used to be illuminated by sodium vapor lamps. You could see it. You could see the light falling on it when you took a time exposure. Now, there is none. And that's because the street lights on my street have all been changed over to full cutoff lights. And
more power to you.
yeah, and there's no light spilling onto the trees. However, in the winter, guess what happens? There's no leaves on the trees. So what do you get? Unfortunately, you get light spilling onto the ground, and many times there's snow, and it reflects back into the sky. So the winter sky is usually brighter, not darker, even though the sky is clearer and crisper. So it's a problem, you know. So Connecticut with this dark sky stuff is pretty cool. And I gotta answer Laura Newbert's question. Laura's wonderful. You know, I work with Laura too. I'm on the show Midnight in the Desert tonight, and it starts. I'm on from 1 to 3 a.m. Eastern time. Okay, and that's with Dave Schrader. I haven't been on Midnight in the Desert recently. I was a couple years ago. And Midnight in the Desert is a great show. If you get a chance to check it out. I did put posts on Facebook and so forth. I go on at 1 a.m. Eastern time, as I said, and I go to 3. We're going to be talking about the search for alien life. We're going to be talking about strange events. I think we're going to be also talking about the implant phenomenon, because I don't know for sure, but I believe that I had one taken out of me by the doctor, and you know, again, I'm a science guy. This stuff doesn't happen to me until it does. Then I have to figure out what to do with it. And on Saturday, I leave for Las Vegas because I got to do a talk out in Las Vegas. And that talk it's a talk I wrote, and it's called Where Does Science Go in the Face of the Unexplained? And so there's unexplained things that happen to a lot of people that we don't know what happens to science, you know. And just a little teaser. I had greyhound dogs, Tycho and Kepler. Go figure, you know, astronomer. He names his dogs Tycho and Kepler. When Tycho was having trouble breathing, I brought him to the vet, and I had the vet rescue him. I did that 3 times. The 4th time, the vet said, it's not going to work this time. You know, the dog has got a blue tongue. He's wide-eyed. He's scared. And I really felt like a jerk for putting the dog through that. So it was time to put the dog down, which we don't put down old people. You know, oh, sorry, Grandpa, it's time to kill you. No, we don't do that. So I have trouble with that, but I know that, you know, they're dogs and so forth, and it's a little different, you know, for me. Well, anyway, I was sitting on a stool in the vet's office and leaning down and cradling Tycho's head. I know some people that actually dropped their dogs off and said, call me after he's gone. It's like, yeah, no. You don't do that to your animal that's been your companion for many years. So when the vet gave the dog this, I forget what it was, I almost want to say phenobarbital, but I don't think that's what, I don't know. Well, anyway, he gave him this drug after sedating him, and the dog, of course, passed away at that point. The reason I know that is because I was sitting on the stool, leaning over and cradling his head. Okay, so I was kind of in a leaned over position. And at the moment that dog died, I got hit in the chest with electricity that knocked me backwards off the stool. And everybody in the office saw it. I mean, this is a matter of public record at the vet. And I literally flew off the stool backwards, and my legs kind of flipped over the top of the stool, and I fell about 3 feet behind the stool. And I thought that maybe I had rolled onto an electrical outlet that might have been on the floor. And that's the first thing I looked for, because I thought I had been electrocuted. I saw lights in my vision. I heard a loud whining, and bam, right in my chest. It was like a high pressure pow, like you got hit with a chest punch in karate. I've been hit like that in Taekwondo, so it felt like that, but it was electrical. And now here's the dog dead on the floor, and I get up like an idiot, running around going, "Did you feel that? Did you feel that?" I literally stepped over my poor dead animal on the floor, saying, "Did you feel that?" to the vet tech, and she's like, "No." And the vet's like, "What happened?" And I explained to him, and no one could understand what that was, and I still can't. And then the year later, actually that sparked the vet to write a 2-page letter to my family describing how the dog was taken care of by us, so well taken care of, given more life than the greyhounds usually get. And it's very nice statement. And then the next year we had to get rid of Kepler in the same way, because Kepler, again, she was actually getting congestive heart failure, and we couldn't rescue her. I felt terrible about it, and so when we actually brought her to the vet, this time I was kneeling on the floor and holding her, cradling her, and the vet gave her a sedative. And when she died, again, I got hit in the chest with this powerful, it wasn't as powerful as Tycho, but I got hit in the chest with this powerful shock, like pow, right in my chest. I didn't know what it was. And when I got hit, it hit me so hard that I was kneeling, remember. I went up on my toes and fell backwards into the waiting arms of the vet tech, who remembered the year before with Tycho. And she said, if it happens, she told me later, if it happens again, I was going to be ready for you. And it did. And she caught me. So it was like, wow. I can't explain this stuff, guys. I don't know what it means. I don't know why this happened. I don't know how to explain it. I just know, look, these are experiences. I don't know how to explain them, but they have to be dealt with. I don't know what they were. And that's the basis of my talk. It's going to be, where does science go in the face of the unexplained? So it was just a very interesting experience. That's all I can tell you. So I know it doesn't leave you much to say there, Daryl. I apologize because.
Oh no, I just said a little bit in the chat on YouTube. Oh, good grief! I'm trying to think of the guy's name. Will Rogers. Will Rogers, American humorist from a long time ago.
Yeah.
He once said, "If there are no dogs in heaven, then I want to go where they went."
That's
okay.
Cute. I like that.
And that kind of says it for me. I lost my 2 dogs. It's been a long time now, but I just haven't had the heart to get another one. I had one dog named Bub. He was a big old double chow mix, plus German Shepherd and Border Collie. Very handsome dog, and smart and personable. And if I ever had a kid, it was Bub the dog.
Yeah.
Well, I lost him to cancer, and I had to have him put down. It just broke my heart. But after he was gone, this prompted me to post that Edie Brickell song, Ghost of a Dog, in the chat room, which is it's a really cool song.
Yeah.
Well, I heard him taking a drink from his water bowl under my bedroom window one night, a few nights after he left me.
Okay.
And one other time, he used to have a habit of coming in and sort of slamming his bum sideways into the side of the bed, telling me he wanted to go out or he wanted to scratch on his butt or something.
Yeah.
He did that once too. I felt him swing his butt and bump the side of the bed like he did so many times.
Wow. Where does science go? The face of the unexplained. I mean, I can't explain it.
Right.
And you can't tell someone that those experiences didn't happen because they're very personal, and those experiences mean something to every single person, But
yes,
I'm amazed. I don't know what to tell you. I mean, other than there's nothing I really need to say, other than it's probably something that did happen.
I'd like to think so.
Yeah.
Hopefully it wasn't just a dream, but
yeah.
I don't know why ghost dogs would need to drink water anyway.
Yeah.
But it sure seemed real to me.
Yeah.
He was a great dog. He was my kid. If I ever had one, it was him.
Sure. I believe it.
Now, carry on.
No, that's all right. This is Praesepe, the beehive, and we're just checking it out. And the dome is a little bit in the way. You can see a little bit of the red light from inside the dome, so you can tell from our view. When I take a look at the view here, you'll see that We actually have it there. There's the moon up there. You can see the moon through the dome there. And we're aiming a little bit onto the dome. And you might, well, I know, why don't we can see if we can actually get to the moon right now, too. You just have to be prepared for the oh, wait, I turned the moon off. Ah! How do I bring the moon back? I don't know how to bring the moon back here. I know.
Now you got it.
I know. The moon is supposed to be right there. Actually, so you know what I'll do? Since the moon is right near Regulus, I'll go to Regulus. Right? Actually, that square represents the size of our field. I think the moon's like right here. What do you think?
Earlier, the moon was immediately to the left of Regulus. They were to the upper left of Regulus. They were very close.
It was like this, right?
Oh, it was even closer.
Okay. Well, you might be right. Let's try that, shall we?
Sure.
Let's go see if we can find the moon now. This will be kind of fun. Hunting for the moon. And in the view here, you'll actually see it get brighter and brighter and brighter. Oh, yeah. Oh, look, there it is. We got it. I think the calculation was good. Let's confirm that, shall we? Let's bring this down. Let's go down, lower, lower. We gotta drop this. Ah, we got it. We got it. Hello. The moon is with us. That's funny. Okay, so I just dropped it down. How about that, huh? Not bad.
There you go.
That was just a guess. Well, thanks to you, we both guessed. Yeah. And we managed to find it. Really cool. I'll bring the moon in now. You'll also notice that the focus will be different even there, but I'm gonna actually I'm gonna try to I'm gonna take a photo and see if what we're looking at is an effect of the video or an effect of actual out of focus, because I've noticed sometimes I can focus on the moon, and when I focus on stars, it's different. Have you seen that too?
I have, yes.
Yeah. So I'll take this one photo, and then we'll take a look at it. Okay. All right. So you see that this photo here. Yeah. Turn off the processing. I did some processing here, so I'm gonna shut that off. Bing. Oops, wrong one. Hang on. Okay, now we turn it off. Okay, there we go. All right, and it's underexposed for a reason. I'm just trying to see. Well, it doesn't look too bad, does it? It doesn't.
It's nice.
Yeah, it doesn't look too bad for the moon.
It's getting close to full.
Yeah, for the bane of astronomers, it doesn't look too bad.
Mark, that's Tycho right there, isn't it?
Yes, it is.
Yeah, just to the lower left of Tycho, you pass two craters.
Okay.
If you might want to go down a little bit. Right there, a little bit below, right there. That crater, we were talking about oval craters the other night. That is one of the true oval craters on Mars, and that's a big one, too.
On Mars?
Schickard, I forget its name.
Huh.
I'd have to look it up, but and possibly the next one over to its left, a little bigger than it, at the edge of the field right now.
Over here?
Yeah, right there.
Okay.
That may also be an oval crater. It looks oval, but that could just be a foreshortening due to the curvature of the moon.
A projection.
Yeah, but I believe that one on the right there is actually one of the oval craters, and I'd have to look it up to find its name.
Okay.
I want to say Schickard or something like that.
All right. Now, just so people understand, most of the craters on the moon are round, and people always say, how come we don't see any oval craters? Well, there's actually a reason why not. When you do see an oval crater, and there's not many, it's because of a very, very low angle collision that gouges out but doesn't create a crater. Okay, it just gouges out something. That's sort of like a low glancing blow without crashing into the moon. If it hits the moon, it's going to be an oval. It's going to be a round crater. And you say, why? Well, The reason is because, actually, you can use physics to figure this out, but rather than that, I'll use an example. Go take a stone and go a skipping stone and skip it across a pond. Every time you see a splash, it's not going to be an oval splash, it's going to be a round splash, even though the rock is traveling at a very low angle across the water. Okay, that round splash is the result of what's called the impulsive force that's striking the water at that very instant. It's moving out in all directions from the strike. It's not moving mostly forward, mostly backward, or to the sides. It's moving out in all directions from the strike. And so every single hit on the water makes concentric circles. Every one of them. You don't get any oval puddles, from that. No oval strikes. So what you can get, however, is when it strikes the water, you can get the water that's splashed up pushing forward with the rock that's being thrown. And that's the same as the ejecta that you see sometimes from craters. When there's some craters that have low angle impacts where the craters have ejecta that goes out to the side, okay, and not much else, okay. And I don't know if I can show it on here. I don't know if we can see it. I might have to take another photo. It's over here. It's right there. This is a Messier. Remember we talked about Messier on
yeah. Messier.
Yeah, Messier. Yeah, we talked about the crater right. Messier right there.
There you go. Right.
Yeah, it's a little fuzzy right now because I have to do critical focus on that. But that said, we're looking at a position where anything that strikes the moon like that is going to be it's going to make a round crater without a doubt. Okay, let me just try something here. Let's do this. Let's move, and I'm getting I can see that I'm also suffering a little bandwidth issue, which is why the screen looks like it's not perfect, and that's okay. Gotta let it settle out. Okay, so yeah, I'm gonna have to let it settle out. However, there is something we can look at too while we're doing this, and that's this over here. You see that white spot?
Aristarchus.
Yep, that's the Aristarchus Plateau.
That is probably my single favorite feature on the moon. It's also the brightest spot on the moon.
Yeah. The Aristarchus Plateau is, I think it's right next to the crater Herschel, isn't it? Is it Herschel?
Herodotus.
Herodotus, that's right, yeah. I almost said Herodotus too. Darn it all, I would have lost points in that test. Yeah, this is the crater Aristarchus, and Aristarchus was made in such a way that it blew this gigantic wad of material off to its side. The crater is round, but because the meteor struck at an angle, it sloughed a gigantic apron off to the side of Aristarchus, making this giant white plateau that's just to its other side here, which is the eastern side. So that issue that occurred there is the reason why we have this white soil. This white material was dredged up in that impact, and it's very obvious. Now, this white material is also very choppy, meaning it's actually not smooth. If it's smooth, they tend to be a little bit darker. The areas like that are lunar highlands, for instance, these areas are actually very bright because of the fact that the moon there actually has a very rough surface. Okay, so let me just go this way with this, and we go down like this. Let's take a photo. Okay. All right, so now you can see a little better. The other thing you can see a little better is some of the color on the moon. Okay, the moon is in color. There's colors to to this little satellite. Now I've got the colors turned up just a little bit. All right, but you can actually see over here, you can see the Aristarchus crater and the plateau right there. And you can see actually a little shadow from the apron. So you see what that looks like? And that's kind of interesting. So it is a bright area. This crater is Copernicus over here. All right.
Yep.
And Copernicus isn't as bright as Aristarchus. But
isn't Aristarchus thought to be one of the younger impacts on the moon also? Most recent?
I'm not sure about most recent. I know that it is considered a younger impact, but
I mean, just one reason it's so bright.
Yeah, I realize that's also possible, and you know, here we have the light reflecting almost directly back at us, so these craters actually show very bright as well. But Aristarchus, you see. That part of the crater is really, really bright, without a doubt.
Right.
You can't miss that. And P&K Science is tuned to doing lunar work, and we're not. So that's why our moon views are nowhere near as wonderful as Paul does with P&K Science, Paul and Keith. And I'm okay with that. I'm not here to give you beautiful moonshots. I'm here to give you excellent nebulae and stuff. But guess what? You know, when we have this thing in the sky, it makes it hard to do that. But anyway, we've been going now for an hour and 43 minutes. And what I have to do, I have to prepare a little bit for this show. So I'm going to have to call it in a few moments. But I wanted to thank you guys for coming out here. Daryl, do you have anything you want to add before I have to stop the stream?
No, not really. Just thanks for having me on, as always. And
well, thank you for coming.
Hi, everybody, and good night, everybody. Glad you came by.
Yeah, no, I'm really pleased that people chose to come out. You know, and we have some people that have been here before. I see Amal's here, Benny Loco, Brainius, D Smith, Dee Dee, W. Tom, and we have several other people that showed up that, you know, contributed in the chat, but they don't show up in the list. And you know, Dave Schmidt's here; he should have shown up. Tony the Night Owl should have shown up. So I don't get why some of the names show up and some don't. That's just weird. It doesn't make sense to me. But that said, I don't know what to tell you. So, if you guys asked a question that I missed, I'm sorry. I see Rockstar was here too. I'm sorry about that, and we'll get to it at some point. You just gotta remind me what it was. All right. So, thank you guys for coming out. I'm gonna go get a drink of water for my throat to just kind of get ready for the next 2 hours on Midnight in the Desert. And I put out on my Facebook page, feel free to, you know, friend me if you haven't. I put out a little notice and notification of Midnight in the Desert, where it's going to be and what we're going to talk about a little bit. And so feel free to join there and check it out. But until then, I just want to say thank you guys for coming out and for making my night extra special. You guys are just amazing, and I don't think I ever want to have I don't think there's a better audience, a better viewers, and better friends than all of you. So thank you guys, and I will talk to you on the next clear night.
Good luck, Mark.
Oh, thanks, Daryl. It'll be fine. All right, all. Good night. Have a pleasant tomorrow, as Chevy Chase used to say. Remember that? Cool. All right. Good night, all.